Hello, in this video we are going to see optimal level of production in the case of perfect competitive market. So the result that we want to show is that in order to maximize the profit, we have to take marginal revenue equal to marginal cost. If you already know that, you can jump to the next video. Okay, in the previous video we have seen that if we want to calculate the marginal cost in this point, we have to take 1 unit of production, let's say 1 bag of wheat, and then this red line is the marginal cost, where the blue line, the slope of the tangent, is the derivative. And so we can see that the marginal cost is below 20, which is this point, and this red line, and we can see the derivative is a little higher, above 20, so it's this blue point. And then if we unite all of the red line, we get the marginal cost function, and if we unite all of the blue line, we get the derivative. And we have seen that if the unit is small enough, then marginal cost and derivative can be considered the same, and this is what we are going to do. Now we are going to introduce revenue, and we are going to consider in the horizontal axis the amount of bag of wheat, and then in the vertical axis money, and we consider revenue as a linear function, and the cost function we justify in previous video why it has this shape. So we can see that, for example, here in this point revenue is equal to cost, so the profit, which is this green function here, this green graph, the profit is 0, and in this point revenue is equal to cost, so the profit is also 0, and we are looking for this point here which maximize the profit. So this value is the value that we are looking for, because this is the quantity of unit that the owner of the farm would like to sell. Okay, let's put some number now. Let's say that the revenue is 25 times x, where x is the number of bag that we sell. So the price of the bag is $25. So we sell 1 bag of wheat for $25. So it means that if we sell 1 bag, we sell 1 bag at the price of $25. So it means that this is the marginal revenue, and in this case this is exactly equal to the derivative, because the function is linear, as opposed to the case of the cost function, where marginal and derivative are similar but not exactly the same. So in this case, numerically, the derivative of the revenue is the derivative of this function here, 25x, and the derivative of this expression is 25, because the derivative of x is 1. And if we see here, the marginal revenue equal to the derivative is this horizontal line that has the constant value 25. So 25 is always the constant slope of this function. So if the revenue is linear, then marginal revenue is equal to the derivative, and is equal to 25, which is the price of 1 bag of wheat. So now we are very close to show this result. So we're going to take a 3.3 quantity of unit, 1 here, and here we can see that the slope of the revenue function is always the same, is 25, so it lies here, whereas the slope of the tangent of the cost function in this point is here, So we can see that the slope is lower than this, and that's why we see that the marginal cost here is lower, in this point, is lower than the marginal revenue. Now, another point here in which we can see that the tangent here is lower than the previous tangent, so that's why the value of marginal cost is going down, but it's going down only up to this point, and from this point on the marginal cost start to grow, because here we can see that the slope is going to grow. And finally, in this point we can see that the slope of the tangent in this point is parallel to the revenue function. So if the slope here is 25, this 25, it means that the marginal cost in this point is going to be also 25. So if we sell this quantity of bag, we can see that one additional unit will provide more revenue than cost. In other words, in this point the marginal revenue, the slope, is bigger than the marginal cost, so we will want to sell more. And up to this point, because beyond this point we can see that the marginal revenue, that is always the same, is the slope, here is smaller than the marginal cost. We can see that the marginal cost is growing up, so we want to sell this amount, because if we sell more than that, then the marginal cost is higher than the marginal revenue. So the slope of this function is higher than the slope of this function. If we see here, we see that the marginal cost is above, let's say here is 30, is above the marginal revenue, which is 25. So this is the optimal point in which we can see that marginal revenue, which is this horizontal line, intersect marginal cost, which is this line. So this is the point, and we can see graphically here that this value, a little above 10, is the point in which the profit is maximized. So conclusion, maximum profit if and only if marginal revenue is equal to marginal cost. So the point in which the profit is maximum, then the marginal cost, which is this, has to be equal to marginal revenue, which is this slope. Both the slope has to be the same in order to maximize the profit. If we want to see this result in terms of derivative mathematically, we see here that profit is revenue minus cost, so which is this green curve here. So if we want to maximize this, we have seen that we have to take the derivative of this green function, and we take the derivative of the profit, and then we force it, and we say the derivative is 0. So in 0 is the point in which we pass from positive derivative to negative derivative. So we find this point. So the derivative of profit is the derivative of revenue minus the derivative of cost, and then we force this to be equal to 0 to find this point. And then we consider that the derivative of revenue is equal to marginal revenue, and the derivative of cost is equal to marginal cost, and we pass this minus to this side. Then we get exactly the same result, but mathematically. Okay, that's it. Thanks for watching, and see you in the next video.